Okay, I think that it looks like a small class today. It's the last class of the semester. Let me start with some announcements. So as I already mentioned a few times, there's the final exam this Friday. Okay, so I'll hand it out through Moodle at around 9 in the morning. It's due 24 hours later. It's open book, open notes. Okay, that's the first announcement. The second announcement is an optional field trip to a local data center. I will be sending around a sign up sheet. We have a room for two groups of 20 students each to go and see a data center that UMass runs. It's a good experience. So if you have the time next week on Wednesday, May 10th, we are planning to go to the MGHPCC, which is the Massachusetts Green High Performance Computing Center. It's a local data center that was being built by a consortium of universities. It's in Holyoke, about 10 miles from here. Okay. Now, the one thing that I will ask for in the survey is if you will need a ride, because I'm not planning to get a bus or anything like that to take us all there. It will be carpooled. So if you need a ride, you need to indicate that, and if I'll see how many people can bring their own cars. It's about 15 miles from here. It's not very far to drive. Okay, so that's something that you should keep an eye out for. I'll send around email with a sign-up sheet. So if you have the time and are interested, sign up. We cannot accommodate the whole class. They can only take two groups of 20, but I'm assuming that many may not want to come because it's final exam week and things like that. Okay. Third announcement is about the course evaluations. I sent an email about this. If you haven't filled it out, please do. The course evaluations are being done through an online form. Unlike the old paper form that we used to distribute in class, this is completely online. It's the exact same form except that you go through a website to fill it out. So I would appreciate your comments on what you thought of the class. I use these comments to make improvements and so on. So please do that if you haven't done so already. Okay. So I have a short class today. Last time we went overtime. This time we'll be well under. So it'll average out one way or another. So we have some material to cover on green computing, not a whole lot. So we'll just go through that and then I will just wrap up the course at that point. Okay. So this is the very last topic in our class, which is green computing. Okay, and when you talk about green computing, okay, it can mean one of two different things. Okay, so the two ways to look at green computing is what's called computing for greening and greening of computing. Okay, so the first thing is greening of computing, which is also known as sustainable IT. So this is broadly the problem of how do you make computing equipment more energy efficient, more power efficient, greener, and so on. Okay, how can you make servers consume less power? How can you make your laptops or other devices like phones consume less power so they have bigger, longer battery life and so on. Okay, and same with sensor devices that we talked about last time that are battery powered. How can you make them more energy efficient? Okay, so this is basically how to design energy efficient hardware, software and system. Some of these techniques are software systems, software techniques. Some of them are hardware techniques. Okay. The other aspect of green computing is what is called computing for greening, which is how do you design software and algorithms and use it. Okay, in other words, how to use computing technology and make something else greener. And I'll specifically talk about, so for example, you can say, can you use algorithms to make transportation greener? How can you make algorithms and software to make buildings greener? Okay, so you can make smart buildings and smart transportation and things like that, where you are using distributed systems, technologies, you are using sensors, you are using software algorithms to make something smarter, greener, and so on. Okay, so green computing has these two facets. Okay, how do you make computing hardware itself more energy efficient, and how can you make other things greener in some shape or form? I'll spend roughly half the slides talking about the first aspect and the other half talking about the second aspect. Okay, so that's basically what we are going to discuss today. Okay, so let me start with a little bit of history. Okay, so energy efficiency of computing has been around for a long time. Okay, and for a long time this was restricted to mobile computing, which were battery powered devices. Okay, and in battery powered devices there is especially a need to make the device more energy efficient, which allows you to increase the battery life of that device. So for a long time it was related to just mobile devices, but more recently this problem has become relevant even for desktops and servers that you plug into the wall that are not run by batteries, but yet you want to reduce their energy efficiency, and a lot of that has been driven by data centers. And I'll talk a little bit about why power is a big problem to address, or a challenge to tackle within the context of data centers, which requires you to make also things like servers more energy efficient, even though they may not be battery powered. Okay, so let's talk a little bit about that. So here is a graph that shows you how the energy bills of data centers have grown over time. Okay, as the new data centers have been deployed, they keep getting bigger. Okay, bigger in space, bigger in terms of the number of servers they accommodate, and so on. Okay, and each server takes a certain amount of power to run. Okay, and if you put more cores into a server, it's going to consume more power. Okay, if you pack more servers into a data center, they cost more as well. And as you will see over a course of so what the graph shows is the dotted line here shows the energy curve, and the red line shows the total cost. And costs have gone up because if you build a larger data center, it takes more expense to build, and if you put more servers as well, it takes more. And if you actually look at the breakdown, you will see that power is actually a substantial part of running a data center. In large data center, electricity bills can cost millions of dollars a month. Okay, so it is a significant amount from a data center's perspective. And here is a rough calculation of what I just said. So let's take a data center of the type that Google or Microsoft or Facebook might build, which are very large scale data centers. Okay, so I'm conservatively assuming 100,000 servers. Okay, these days they have started building data centers that can have 500,000, million servers and so on. Okay, so if you take the monthly cost of a server, it is a rough calculation. So assume that the server consumes 500 watts, okay, which is a rough figure. So now if you see if the server is on for the whole month, if it's consuming 500 watts of power, then you say 500 watts times the number of hours, and you divide that by 1000, that gives you cost per kilo, and then you multiply that by cost of electricity, which I'm assuming is 10 cents per kilowatt hour. So you're just saying how much energy is a 500 watt server going to consume for the whole month. Okay, and then you multiply that by cost of electricity, and it comes to around $50. So that's the bill that a single server is going to cost you, okay, every month. Then you basically say 100,000 servers, so you multiply the two, you'll get 5 million. Okay, so that's basically the electricity bill of just powering the servers. Now a data center, if you have that many servers, will also have a very large cooling infrastructure. All of these servers will generate heat. Okay, so a large amount of your power bill also goes into cooling the data center, and in less efficient data centers, for roughly 1 watt of power that the server consumes, you need 1 watt for cooling it. Okay, effectively that has doubled your data center cost. Now Google and others have tried to reduce the cooling. They can't reduce the number of servers because they still have to serve load. You might be able to make it a little more efficient, but what they can do is make the cooling more efficient, and that can reduce your bill. But if you assume 1 watt of power for 1 watt of electricity, then your bill has just doubled. Because for every watt that you consumed here, you have to put an air conditioning infrastructure to cool all of your data centers. So you basically ended up doubling it. And so, so there is a metric called PUE, which is power usage effectiveness. I introduced this when I was talking about data centers and cloud computing a few classes ago, which was the total IT cost, okay, of running everything, which is cooling and computing and so on, and you divide that by just the cost of powering your servers. Okay, and you have for most data centers, PUE numbers are in the range. That's a ratio. Okay, the ratio is around 1.8 to 2. Okay, ratio of 1.8 says for every dollar you spend to power a server, you spend 80 cents to cool it and do everything else. 2 essentially says for every dollar you spend to power a server, you're spending another dollar to cool it and do whatever else you need, like networking and so on. Okay. Now Google and others run some of the most efficient data centers that you can find today, and their PUEs are in the range of 1.1 and 1.2. That means the cooling overhead is barely 10% of what the server power consumption is. Okay? And I'll say why that is the case, and a lot of it has to do with not using air conditioning at all. It's using other forms of cooling. Okay? So the lower your PUE, the more efficient your cooling infrastructure. Server infrastructure can itself be made more efficient as well. But this should give you some sense of why companies are very interested in making data centers energy efficient. If you're paying $5 million a month on your electricity bills, you have a strong incentive to say what can you do to reduce that bill. Okay, and so we'll talk about data center power management techniques. Okay, so how can you go about reducing your electricity bill? Somehow, if you can reduce the cost of powering your servers, your bill will come down. Okay, rather than paying $50 a month, if you made it $45 a month or $20 a month, your basically bill is going to go down. Okay? If you reduce the cooling cost of your data center, okay, also your costs are going to come down. Okay, and then if you adopt some other green practices, and we'll see what they are, also you can further reduce your. So people have looked at all sorts of different techniques to make data centers greener and more energy efficient. Okay, and by the way, green and energy efficient are not necessarily the same thing. Okay? When you say something is green, you might talk about its carbon footprint, not just its energy footprint. Okay? Carbon footprint also looks at where your electricity and other sources of energy are coming from. Okay? So you might have a data center that consumes a lot of electricity, but if all of your electricity is coming from a renewable source like wind or solar, that's considered to be a green data center from a carbon footprint standpoint. It may not reduce your electricity consumption, but the electricity that you're consuming is coming from green sources. Okay? So there are two slightly different things. You might be able to reduce the electricity bills, and yet your electricity may come from natural, so not natural, but non-renewable sources like natural gas and others. Okay? So people have looked at both reducing energy footprint as well as reducing carbon footprint. So here I'm only talking about energy footprint for now. We're just trying to reduce the electricity or power consumption in your data center, not necessarily make it greener. We'll talk about that as well. Okay? So how do you reduce the cost of running a server? You could actually design your hardware to be more power efficient. Okay, you can put low power cores. You can put RAM that takes less power. You can try to do other things that will reduce the power consumption, and many of these data centers actually do that. Okay, so Google, for instance, does not go and buy servers from a standard vendor. They design their own servers that are specifically designed to reduce the power usage as much as possible. Okay? So they go to the extent of even building their own servers just to cut the power usage. Because even a 10% reduction will mean a substantial amount of savings, as you can see based on the numbers I showed you. Okay? In some cases, they build the servers to run on DC rather than AC. Okay? Because in a lot of the servers, okay, you will have a power supply. The power supply takes AC and converts it into DC. That's the same thing that your charger will do. Okay, the charger is taking AC and outputting DC, which is what is powering your machine. But the AC to DC conversion will come with some loss, with some power loss. So if you actually have a server that runs directly on DC, and you have a source of your power infrastructure is just supplying DC power, you can reduce some of the conversion loss. So they have even gone to the extent of, and Facebook has actually done quite a bit of work on that. Many of their servers actually run on DC, they don't run on AC. So they don't have inbuilt power supply that do the conversion, they take direct DC input. So a lot of work on making either the CPU cores more efficient, the power supply is more efficient, making the RAM more efficient, and so on. Okay? So that's the hardware level techniques that people have looked at to make servers efficient. You can also do things in software. Okay? You can build intelligent power management techniques. Okay? So for instance, in the night when the load in your data center is really low, okay, why not turn off some of the servers? Why keep them on and consume power? Okay? That's one simple technique that many of the data centers do. So intelligent power management, which is as simple as turn the servers off when not in use. So we can use virtualization to move VMs around. Okay? In the night, you can take all your VMs and pack it into a smaller number of servers, turn off the remaining idle server. During the day, you move them back to where they were. Okay? So you can do things like that. So those are all software techniques that have been designed, and there are lots of them on intelligent power management, scheduling for power, and things like that. Okay. I should also mention one curve which is called the energy proportional curve, okay, which is another reason why. So this is called, actually it shows us that servers are not energy proportional. Okay, this is called energy proportionality. Okay. So this is on the x-axis is load, okay, or utilization of the server, okay, and this is power consumed. Okay, so what the simple curve is showing you is that first thing it says, as load goes up, the power consumed by the server goes up. Okay, that you can imagine. If you have more load, the server has to work harder. Okay, so now that's the first thing. But the second thing it shows is when the load is zero, the power consumed by the server does not go to zero. Okay, if you had hardware that was fully energy proportional says that the energy consumed is directly proportional to the load. The ideal curve that you want should actually go to zero. It should be like this. Okay, which says if the load is zero, then the server shouldn't consume any energy because there's no work to do. But that's not how servers work. Even if there is nothing to do, the server is on, it's running, it's going to consume some power. Okay? So from a hardware designer standpoint, the holy grail of designing energy efficient hardware is to make it fully energy proportional. Okay? So now that you cannot do with current hardware. So the actual curves look like the top curve, which is even when the server is idle, it will consume some power. In fact, servers today can consume as much as 40 to 60% of their peak power. So let's say this is peak. This is 100% utilization. This is the max power. At zero load, they still consume 40 to 60% of the peak power, which means if the server is sitting there idling, it's still taking 60% of what it would consume. It was fully loaded, which means all of that energy is wasted. So a lot of these hardware design techniques that I talked about also look at how do you make the curve more energy proportional. Okay, how do you make the curve basically start from as close to zero as possible. Okay. Now, if you take any computer architecture class or any hardware design class, you will learn more about that. That's a hardware design technique. You can't do anything from a software standpoint in this case. Yeah. So making the system more energy proportional will automatically reduce the need for any software technique, because it was fully energy proportional. If the server is idle in the night, it will consume zero power, then you don't need to do any power management at all. Because this hardware is not energy proportional, do you actually need to do things like turn off the servers when the load is zero and so on in order to actually make it consume zero power. Okay? Okay. So that's reducing server power. Now there are also ways to reduce the cooling energy used by a data center. There are many different techniques used here. And one is you can make the air conditioning system more energy efficient by making the compressors of the AC more energy efficient and so. That's a mechanical engineering problem. Okay, not a computer science problem, but you can build better, more energy air conditioner. Another thing you can do is actually improve the airflow in your data center so heat is dissipated with less energy. Okay? And that is shown in this colored picture here, which is really a heat map. Okay? And if you come to the optional data center tour next week, you will actually see some of this. Okay? So you will understand how cooling works. So what is shown here is that the dark blue things here are actually aisles of server racks. So there are racks of servers, and the way they work is that all servers take cold air from the front, and then the air actually flows through the server and hot air comes out where the heat has actually been dissipated through airflow. Okay? Now if you build better airflow techniques, and then this hot air that has actually been dissipated has to be removed by the air conditioning system to cool it. Okay? So you essentially, a cold air goes into the server, hot air comes out, that heat has to be then taken out of the room through an air conditioning so that the room stays cold, otherwise the room will start heating up. Okay? Now there's a lot of thermal engineering techniques that have been built. That is, how do you take the heat out with the least amount of work? Okay? By building better airflow. so that the air is actually flowing out into the air conditioning system and is taking it out as efficiently as possible. Okay. So a lot of it has to be dealt with thermal engineering, and so people have looked at that. The other thing people have looked at is you can actually think about how to put load on the server. So if you have 4 racks of servers as are shown here, if you put all the load on the first rack, okay, this rack will overheat and those other racks will be cool. Okay? And cooling is non-proportional. I mean non-linear, not non-proportional. It is proportional, but non-linear. The more the heat, the harder the AC has to work. Okay? So if you uniformly raise the temperature of all our racks by 5 degrees Celsius, then it might take less power than if you just raise 2 of the racks by 10 degrees Celsius. Because as it gets warmer, it costs more. This is obvious from your experience with air conditioning. In the summer, your air conditioning bills go up because your air conditioning AC is working harder. Okay, so it's a non-linear relationship between how much heat the air conditioner has to take out versus how it is spread. So you can actually spread the workload through workload placement techniques or VM placement techniques. So there's gradual increase in temperature, not sudden spikes or no hot spots or real hot spots, meaning temperature hot spots. As you can see in some of these cases, you'll see the green part says that those servers are not working as hard, and the orange parts are servers that are more loaded, and so on. So there's a whole lot of thermal engineering that goes on into reducing the energy bill. Okay. The other thing is to actually not use air conditioners at all. Okay. Rather just use what is called open air cooling or free cooling to cool your data center. Okay. So in this case, rather than putting a gigantic air conditioner to cool your entire data center, you assume that the data center is in some cooler climate and the outside air is actually cooler than the inside air. If you could do this, then you could simply take the cooler air and just circulate it through the system and cool your data center. This is not unlike you opening your windows in your house to let fresh air or cool air come in and cool the room inside. Of course, you can't do this on a hot day when it's hotter outside than inside. Then you will actually heat up your room rather than cooling it. Same is true here. Free cooling can be only done when the temperature outside is cooler and is less humid outside. Okay. So in many cases, these data centers are actually designed to be placed in cooler climates where you can take advantage of outside cooling. The data center that we have here in Holyoke uses that for 9 months of the year. Okay, because we live in a cool enough climate that the outside temperature is cool most of the year except in the hot summer months. So you can actually use cooler outside air to cool your data center rather than Facebook does it as well. They actually literally pump cold air into their data center from the outside. Okay, they put their data centers in northern parts of the US where it's colder, not in the southern parts where it's warmer. Okay. Now, if you could do that, then you don't need an air conditioner for a lot of the time, which will reduce your cooling bills. Okay. So those are all techniques that have been used in data centers to actually cool the system more efficiently or with lesser cost. Any questions on this? Okay. So that's the data center part. Now for the rest of the few slides that I have, I'm going to switch gears and talk about IT or computing for greening. So the first few slides were how do you green computing, which was data centers in particular. And I talked about hardware techniques very briefly, software techniques and cooling. And now I'll talk about how can you take algorithms and sensors and other devices and use it to make something else greener. So I talked specifically about smart buildings, smart transportation, but I'll give the case study will be focusing more on smart buildings. Right. Now, the reason I've chosen smart buildings is buildings are now actually considered to be an example of a distributed system. Okay, any modern building, any modern office building will have lots of embedded sensing in it. There'll be computation everywhere that's monitoring every aspect of the building. Okay? There are sensors in this room that track motion. There are sensors that actually track the temperature and control airflow and so on. And there's a infrastructure that decides where to turn off lights and where to how to cool each room or each floor individually and so on and so forth. Okay? So when you have a lot of sensing and computation, okay, you start looking like your infrastructure starts looking like a distributed system. Now this distributed system doesn't necessarily have servers. Your computing elements might be much smaller embedded nodes. Nevertheless, they are computing elements. Okay, so you can look at buildings as an example of a distributed pervasive system that I introduced in the last class, where your sensors that monitor energy and occupancy. Occupancy just says what parts of the buildings are occupied. They can monitor temperature, humidity, keep the building comfortable, and so on. Okay. And then the sensors will produce data that you can analyze in real time, okay, and then use it to do what is called actuation, okay, or control. Okay, which says if the room is too cold, then warm it up, or if the room is unoccupied, turn off the light, or the moment somebody walks in, you want the lights to turn on automatically without having them to turn lights on and so on. Okay, so this is also referred to in many cases as a sense, analyze, respond type system. So many examples of whether you're smart transportation or smart buildings or other kinds of smart things, you follow this cycle where you send some data, you analyze that data that's coming from the sensors in real time, and then you respond through some actuation or control. Okay, and then that will basically complete a loop where then you'll continue to sense and you'll continue to act based on whatever you're observing. Okay, so now let's take a look at specifically buildings and see how smart buildings work, what kinds of sensors are in buildings and so on. Okay, so here's a more detailed slide that shows you the sense, analyze, response loop, where the analyze part now has become fairly sophisticated in modern buildings. You can use things like machine learning or very smart algorithms that can analyze a lot of data, try to understand what's going on, and then use that to do control. Okay, so that's the sense part, and this is actually a loop, although it's not only shown as a one-way flow. The control then actually changes the environment, so you start measuring and monitoring new things, and you can do more analysis of it and so on. Okay, so let me give you some examples of sensors that you can deploy. Okay, so those pictures actually show you some sensors that you can go to a store and buy today. Okay, so the top one is called a kilowatt sensor. It can actually monitor the power usage of an outlet. Okay, so this one actually has a plug of this point. So you put it into any outlet, then you plug your device into this. Okay, and it's simply measuring how much electricity is flowing through the wires. Okay, and the display there shows you how much power or electricity any device is consuming. So if you simply wanted to monitor the power consumption of a single device, you could buy a sensor of this sort. It costs about $20. You can go to Home Depot and buy it. Okay, it's just available off the shelf. So early sensors basically used what are called outlet level sensing. This one is an external sensor, but you can actually buy power outlets that have these kinds of sensors built in, and they will report to you how much electricity is being consumed by that device. Okay. So the early ones only showed that on a display. Then the later ones have capability like Bluetooth or Zigbee, so they transmit that to some central node, so you can actually see that the power consumption remotely. So if you have a set of these outlets and you're plugged in, let's say your refrigerator, your dishwasher, or whatever you're monitoring, you can actually get on a dashboard power consumption details of how much energy was consumed by each of your devices. Okay. Now these are just very rudimentary sensors, but something that you can just go and do play with yourself. Okay, modern ones will actually be already embedded into the infrastructure. Okay, and here is an example of something that's embedded into the infrastructure. Okay, so this is the circuit breaker panel that you might see in a typical house. Okay, so these are actually circuit breakers, or what you call fuses, that will allow you to control individual lines, power lines through your circuit. Okay, what is shown here, which may not be very visible, is that there are sensors that have been clipped onto these wires. Okay, so what this will do is they will basically, you just clip it on, and it is just measuring electricity flow through that wire. So now you can actually get the power consumption of individual circuits. So if there's one circuit for a dishwasher, it will tell you how much power it's consuming. One for let's say your laundry washer dryer, it will show you how much power that's being. consumed and so on. So this is monitoring at a circuit breaker level. So you don't have to go and monitor individual outlets, but you can monitor individual circuit breakers and so on. Okay? So this is what you will see in a lot of modern infrastructure, where at different points in the power distribution, in the wiring, you will actually have sensors that have been attached that will monitor how much electricity is being consumed within that segment. Okay? Now that segment might feed multiple devices. Okay? Each of those circuit breaker may feed several outlets or several switches. So you are not getting full, very fine grained sensing, but you are getting sensing at a granularity of individual circuits. Okay? So that's an example of an instrumentation that's been deployed in a smart home. This is this picture here. It's a little grainy, but it shows you the clamp that you actually put on these sensors, on those wires. Okay, you don't have to actually cut the wire and put a sensor. You simply clamp it on the wire. It's just measuring magnetic field, and from magnetic field is inferring how much electricity is flowing. Okay, so I'm going to show you, if I can make this work, an example of how this device. So these devices can then report your okay, so here is a web dashboard for one of those sensors. So this curve here is showing you the power consumption of the entire home, and you will see that there are different check boxes here. So if you check the washer, it doesn't show anything. Let me look at. Okay, so I think maybe the fridge might show something. Okay. So I checked this fridge box, and then you see the green curve here is just saying the circuit breaker that the refrigerator is on is consuming this much power at different points in time. This is the total power that's consumed by the house. Okay? And each of the circuit breakers like microwave and dryer, they have been also configured, and each of them is being tracked individually. So you can get a sense of how much electricity is being consumed by the house, what circuits are consuming how much power, so you can get a breakdown of what appliances are consuming how much power and so on. Okay? It's a very simple example of what a very standard and this off-the-shelf sensing device can do based on this kind of monitoring. Yes, question there?
Granularity of the measures.
What is the granularity of the measure? So to some extent that depends on the hardware. Some of these hardware can do 1 second measurement. Most of them will do one measurement every few minutes, like 1 minute or 5 minute granularity. So you can actually get a fairly detailed power usage patterns for any homes.
So you could, for example, move the load, like for example, stop using the fridge for the peak hour and move the load to like a less expensive time of the day or something like that.
Okay, the question is, can you move the load from one time period to another? So this, what I showed you is a simple monitoring infrastructure. It doesn't do any control. It is simply telling you how that user or users in the house consume electricity based on their normal pattern. It's not doing any optimization. Okay? The optimization will come. So this is what I was saying, right? So that's just the sensing part. Analysis and control is the next part that you build on this. Sensing is just going to tell you what's happening. It's not going to tell you how to change anything. Okay? So the example you mentioned was if you have different electricity prices, like evening you have peak pricing and morning during the day you have lower prices, which still most electricity companies don't do. They give you flat pricing, which means the cost of electricity doesn't change from 1 hour of the day to another. But there are some places where the pricing is variable. In the evening it costs more to consume 1 unit of electricity than maybe during the night. So in that case, a smart building could say, can I move some of my consumption to a lower price period and reduce my bill? Okay? Data centers and other very large consumers often get variable pricing. Okay, but not necessarily homes. But yes, if you had it, you could do optimizations like that, which I'm going to talk about. Okay, so the next step is to then take that sensing and analyze the data, which tells you what actually is going on in your environment. So in the context of large office buildings, all of those buildings have something called a building monitoring system, or a BMS. That's the control infrastructure and the monitoring infrastructure for the building. Okay? Many companies like Siemens and Johnson Control, they build these building monitoring systems, and they will basically deploy one, which will be a large panel that you will see at the entrance of the building, which has all sorts of sensors that are monitoring all aspects of the building. And then you can control many aspects of it through that building monitoring system. You can say, okay, turn off cooling on the third floor, and then it will just basically make the air conditioning stop providing cooling to the third floor. Or you could say, turn off the lights on this hallway, and you can, so all of it is centrally controlled. In a house, you don't have that kind of infrastructure, but all office buildings have this kind of more centralized control infrastructure that allows you to control what is going on inside the house. Okay? Now, the question that you had asked was, what do you do with all of the sensing data? Why do you want to put so many sensors? The main purpose of putting all of these sensors is to understand the usage patterns, okay, and try to see if you can optimize it somehow, because we are talking about greening of using IT to do greening or computing to do greening. So the question you want to ask is, how can you reduce your electricity bill if I could sense what is going on? Okay, to some extent you want to do that automatically, not ask the user saying, okay, don't do these things at this point, do them at other times, and so on. Okay? So a lot of this research around this area has focused on how do you do modeling, analysis, prediction, how can you use statistical methods or data-centric methods like machine learning to learn what is going on inside the house when certain activities are happening. Can you then optimize the usage? And there are many things you can do to optimize. First thing is, if I can use sensing to identify waste. Okay, the waste says, okay, there's nobody in this room after 10 in the morning to noon, but the lights stay on. Okay, that's a clear waste of electricity because somebody forgot to turn off the lights. That is easy to automate, because if you have remote control lights, somebody fails to turn it on, if there's no motion being sensed, you should turn it off. Okay? Now your sensors will tell you that this is happening repeatedly. And so if you then put in algorithm that say, okay, monitor the motion. If there's no motion for 10 minutes in a room, turn off the lights. That is going to save you some energy. Now you can do the same thing in a more sophisticated way for heating and cooling, which is where a lot of the energy goes. Lights only consume around 20% of the electricity bill of a typical home or building, 10 to 20%. Heating or cooling, air conditioning, heating takes around 50%. So if you could do the same thing for heating and cooling, which is you leave your home to come attend classes, but you left your heating or cooling on. Okay, now it's wasting energy. Okay? If your thermostat could detect that there is nobody in the house and then turn down the heating, then you saved on your energy bills for your house. Okay? So you could basically do all of this analysis to reduce your energy bills. Okay? So here are some of the questions that this research asks, which is, is your furnace, heater, dryer inefficient? Okay? Are you paying too much to do your laundry, which might have a 20-year-old washing machine, and if you go and buy an Energy Star machine, your bill for that appliance might go down and it might pay for itself in a few months. Okay? So you could ask that question. You could ask, is your air conditioning schedule aligned with occupancy pattern? Are you running your AC when people are in the building? Okay? Either is, if you are heating or cooling when there is no one in the building, you waste electricity. If you are not heating or cooling when there are people in the building, then you make the people uncomfortable. You start feeling that the room is too hot or too cold. Okay? So you want to keep the environment comfortable and you don't want to waste. So you want to optimize it from both perspectives. So that's one that's looked at. And then there are these questions of, if you have peak usage rates, then how can you optimize the bills by doing things at off-peak and so on. Okay. Now, also there's a lot of research on how can you incorporate renewable energy better into smart buildings. Okay. So if you had solar, rooftop solar or wind and so on, how can you better incorporate that? The main challenge with using renewables is they're intermittent. Okay, so that's one issue. You will hear this term intermittent, which means if you put solar panels, and this building actually has solar panels on its roof, the electricity produced by the solar panel will continue to fluctuate. First of all, during the night there is no solar. Okay? But even during the day, as the weather changes from sunny to cloudy, the electricity output of your solar panels will dramatically change over time. Okay? That depends just based on how much energy is being produced. And here is a graph that shows you for different days how much electricity a panel produces. You will see that on cloudy days, the peak usage, peak generation is maybe 1/10 that of a sunny day. Okay? And that's just on characteristics of how solar panels work, how much, depending on how much light they receive, sunlight they receive, they'll produce different amounts of electricity. Okay. Now, one question you could ask is if you deploy your own solar panels, how can you make the best use of the electricity it's producing? Okay. So you'll have to do one of two things. First is you want to align your usage to when it produces electricity. Okay. If your solar panels are producing a lot of electricity during the day, but you are in the office during most of the day and doing nothing at home, then no, you are not directly using that electricity yourself. But when you come home in the evening and you start doing things like your laundry or just cooking, there's no solar at that point because the sun has already set. Okay? So one big challenge for many people who have 9 to 5 schedules is the solar production and their usage are not aligned. They're completely misaligned, as a matter of fact. Okay? So how to deal with that is an interesting challenge. There are many things you could do. Some have advocated use batteries to store the electricity and then use that at a later time, use inverters. Others just say if you have excess electricity, feed it to the grid and let somebody else use it, and you get paid a little bit of money by your electricity company for feeding some electricity to the grid. So there are many aspects of this that you can look at. The other one is the kind of question you asked, which was if I could forecast how much my solar arrays are going to produce, can I align my loads better to it? So for instance, if I just load my washing machine and say run it whenever there is enough solar, okay? And so you just go to work and let your smart home decide when to run the washing machine. By the time you come back, your clothes are washed, but you don't care when exactly, and let it decide based on when you generate solar energy and so on. So these kinds of scheduling algorithms have also been looked at to further make some of this better. Okay? It requires you to have some prediction capability to say how much are you going to generate today or tomorrow, so I can schedule something in an intelligent way. Okay? For this, you might have to look at weather forecast to do predictions automatically and so on.
I have a question.
Yeah, sure.
From the regulation standpoint, now that there's a lot of microgrids, is it possible to send energy to other, buildings?
Okay. So question is, if you have extra electricity from your solar panel, is it possible to send it to neighbors and so on and have them consume? So in most countries, even though you may not have this notion of a microgrid, there is something called net metering. What net metering says is the utility company is required by law to accept excess electricity that you can feed to the grid. Okay? So your meter can run both ways. If you are feeding electricity, your meter runs backwards because you are actually consuming negative power, essentially. Okay? And when you are actually consuming power, your meter will run the normal way. Okay? So, and the assumption is if you actually feed into the grid, then that electricity flows to any of the neighbors that are actually consuming electricity. Okay? So this is happening automatically through this notion of net metering, which basically says that if you have excess power, don't shut down your, if you couldn't feed the grid, if you have excess power, you would essentially shut down your solar system, because the electrons have to flow somewhere. Okay? Either you have to put it in a battery and store it, or you simply shut it down. So rather than either making you either buy a battery or wasting your electricity, most utility companies will accept your excess electricity, and then that will just naturally flow to your neighbors. Okay? So that is done in many places automatically. Yes, your question?
You've got solar thermal up there. it's not something that seems to be talked about much these days. Is there still active development and deployment of solar thermal?
Okay, so question is about solar thermal. Solar thermal simply means you use a solar panel to heat your water. Okay, there are many countries where that is a very common thing to do. For example, if you go to Asian countries, there are more solar thermal installations than there are solar arrays, because it's expensive to heat water and you just put a solar water heater. Okay, that's what it is. Even here it is picking up steam, but well, that's not the right word to say. It is picking up, but rooftop solar has gone way beyond solar thermal because there are more incentives here than there. Okay? It's just a matter of incentives. If you could have put more financial incentives for solar thermal, and people will say that's cheaper for me. So I think there are, because of the incentive structure, if there are no incentives, then people will say, well, how much investment do I make and what do I get? So right now there are a lot more incentives or subsidies for solar arrays, but they do exist and there are people who use them from time to time. They are not as common as solar, rooftop solar. Okay. All right. So last slide is about people, which is important component of this. So you cannot make your any smart home or even a regular home energy efficient if people are not conscious of their energy use and do something consciously. Okay, so there is a lot of work that says how do you change people's behavior and make them more energy conscious. Okay, this is a harder problem in many countries where energy costs are cheap. Okay, if it only costs you 10 cents a kilowatt hour and your monthly bill is $30, turning off lights might save you 5 cents. Okay, that may not be worth people's time, or they don't actually, they are not as conscious than if the costs were 5 times as much. Okay, in many other countries where price of electricity is higher, people are a lot more conscious of their electricity usage. But in some countries here, like in North America, that's not as much the case. So then the question is, how do you incentivize people to be more energy efficient? Obviously, monetary incentives are the best, but monetary incentives make sense when the prices are high enough that the incentives matter. Then you have to provide social incentives which say, okay, you basically, I'll just tell you that being green is good as a citizen or being part of the community. I will tell you what your usage is, and maybe you can use that to make your lifestyle decisions to be more greener in some shape or form. Okay? So motivating people is just as important as designing smart algorithms, because you can make anything smarter, but if people say I don't care and don't use it, then none of this is actually going to work. Okay? Which is what happens in many cases where you put a lot of technology but people just don't use it because there isn't enough incentive to use it at all. Okay? Or they think it's too complicated to use, which is also a problem. So providing good feedback and incentives to people is just as important for any mechanism to do greening, whether it's smart building or smart transportation and whatnot. So with that, I'm going to wrap up. We are a little bit early, as I said. So this is just a slide that summarizes all the topics that we've covered. Okay? Every one of these topics is also on the final exam. As I had mentioned, final exam is comprehensive. It will cover everything that we have covered since the very beginning. There will be a little more emphasis on the part after the midterm because you've not been tested on it at all. But everything is fair game as far as the final exam is concerned. Okay? So just a quick recap, we started with broad architectural discussions of distributed systems. We looked at peer-to-peer, client-server, and so on. We then spent some fair bit of time talking about RPCs, RMIs, whatnot, and distributed communication. Okay, then we looked at threads, we looked at scheduling processes, scheduling in distributed systems. We looked at virtualization, what it is, how it is used to do various optimization. Okay. Spent one class talking about distributed naming, DNS, directory services, LDAP, and so on. And then we spent a several sequence of lectures talking about a whole slew of classical problems in distributed system. Things like leader election, distributed transaction, clock synchronization, GPS, and the whole then consensus and so on. Okay? And then we spent some time talking about consistency models and fault tolerance. We talked about the Byzantine general problems, and we talked about two-phase commit, three-phase commit. Then we also discussed consensus problems such as Paxos and Raft and so on. And then the rest of the class was spent talking about distributed file systems, distributed storage systems, and in the last 2 hours, and then we talked about distributed middleware. Okay? I went through a whole bunch of them very quickly, but we talked about Corba, we talked about DCOM, we talked about Genie, I talked about distributed middleware, distributed data processing systems like Hadoop and Spark 2 classes ago. Then we spent some time talking about security. I talked about authentication, I talked about encryption, we spent some time talking about electronic cash and Bitcoin and things like that. And then today and part of last class we were talking about distributed pervasive systems and green computing. And over the course of the thing we also spent some time talking about web, streaming and cloud computing. So that's one class slide snapshot of everything that we covered. Okay, so I think as far as the course is done, we are the course is concerned, we are done. For those of you who came in late, I did announce that as you all know, exam is on Friday, and next week there's an optional field trip to a local data center. If you want to go see what a data center looks like, see how their cooling works and what the servers look like, etc., you're welcome to come. There's room for about 40 students, not the whole class. Okay, I'll send around a sign-up sheet. If you have time and interest, you can come. There is no requirement. It's completely optional part of the course. Okay, so with that, I'm going to wrap up here. Okay, I assume you learned something from the course, and I would appreciate it if you went and did course evaluation and let me know what you thought of the course and suggestions for improvement and so on. Okay, all right. So let's stop. And I will wish you all luck with the exam and have a good summer.